Hey everyone, this is Josh from Ahead of the Curve Tutoring Services. I'm really excited to announce the start of our new video walkthrough series. In each video, I will be taking common problems that my math and science students are facing and breaking them down into easy steps with reliable setups. I encourage you to grab a pencil and follow along, and feel free to go back or pause the video if you missed something. And remember, whether you're struggling in school or just want to get ahead of the curve, we have tons of amazing options available. Book a session with us now. Okay guys, our first video is going to focus on solving trigonomic equations. Let's get started.
All right, guys, so a lot of my students in grade 11 and 12 university math are having a lot of troubles with trigonometry in general, and I totally get it. It's an extremely abstract way of thinking. Now that you're taking your normal XY plane and putting angles on it and thinking about certain ratios and thinking in multiple quadrants, it's a lot to handle, I understand. So today I want to kind of go through a little walkthrough on how to solve more difficult trig equations. I could start with an easier one, but I think an example like this will kind of best exemplify my process of how I solve trig equations, and I think it'll be very, very useful to all of you guys too. So before I start solving this trig equation here, I think it's just important that we get a little guideline down on how to solve trig equations in the first place. And the best thing to do is to draw this little unit circle study guide that I'm going to give you right now. So here we go. So here's your normal XY plane, but now we're going to start putting angles on it. So I know that all angles are measured in standard position from this point right here. We'll call this our 0 mark. From here, we always measure angles counterclockwise from standard position. So we know that if we go a quarter turn this way, we'll be at 90 degrees. Or if you're taking grade 12 advanced functions, I know you guys use radians more often than degrees. So 90 degrees is the same as pi over 2 radians. Rotate again. We're left with 180 degrees or pi radians. Down here, we got 270 or 3 pi over 2 radians. And if we wrap it back around full, we're left with 360 or 2 pi radians. Okay. And then we know that this is quadrant 1, this is quadrant 2, this is quadrant 3, and this is quadrant 4. You guys also learned a cast rule. The cast rule basically tells you which a quadrant a trig ratio is positive in. So in quadrant 1, we should know that all trig ratios are positive. In quadrant 2, just sine. In quadrant 3, just tan. And in quadrant 4, just coast. Here's your cast rule, the CAST. Then finally, what I'm going to do is, you guys should have learned that for any terminal arm you draw on a unit, a circle, you can measure two kinds of angles. You can measure a principal angle and a related angle. I'll just do a little example here just to show that. Let's say I have an arm in this quadrant here. I know that the principal angle, which I'm going to call theta, is always the angle from standard position all the way to the arm. That's theta. And then there's also another angle called theta r, or the related angle. And the related angle is always the angle between the arm and the x-axis of the quadrant that the arm is in. My arm is in the third quadrant, so my theta r would be just from here to here. And now, given kind of angle rules and stuff like that, there's always going to be a relationship between theta and theta r. So we are going to kind of summarize what those relationships are in each quadrant. So in quadrant 1, the angle theta and the related angle theta r are going to be the same thing. In quadrant 2, I'm just going to use the radian measure, but this would work the exact same way for the degree measure as well. Theta is going to equal pi minus theta r. In quadrant 3, theta is going to equal pi plus theta r. And in quadrant 4, theta is going to equal 2 pi minus theta r. So now what we've done is, if we can look at a trig equation and determine which quadrants the answers will be found in, we can simply use these relationships here to take our related angle that we're going to solve for and then apply it to get our actual answers to our problem. All right, so let's get started. Okay, so first things first, I'm just going to move this guy over here. There we go. That's good. All right. So whenever we're solving a trig equation, the first thing we want to do is get the trig expression by itself. And by that, I mean, I want to basically isolate for the sine expression or the cos expression or the tan expression. So that just takes some basic rearranging. So we'll move over the 1, and then that's going to lead us to this here. I move over -1, 1 plus 1 equals 2. And then my trig expression is almost on its own. There's still this 3 attached to it, so I'm going to just divide both sides by 3. And here we go. We get sine of 2x minus 3 equals 2/3. Okay, so now we're in a position where we have a trig expression equivalent to some ratio. Once we get to this point, we want to start setting up our equation. So the way we're going to do that is we're going to look at our ratio, and we're going to determine if it's a positive ratio or a negative ratio. Obviously, 2/3 is a positive ratio. So from there, we're going to ask ourselves, in which quadrants is sine a positive ratio? Looking at our unit circle here, sine is positive in both the A quadrant and the S quadrant. So I know that sine is positive in quadrant 1 and quadrant 2. I know in quadrant 1, theta is equal to theta r, and I know in quadrant 2 that theta is equal to pi minus theta r. Now I've set my quadrants up. Now it's just my job to find the value of theta r, and from there I can get some answers. However, if you look at our trig expression here, we'll notice that there isn't a theta here. We have an expression of a 2x minus 3. So what I want to do from this point is when we're solving this trig equation, we're going to actually solve it in terms of theta first, so we can best make use of this unit circle here. Then after that, we can easily just make a resubstitution back in to solve for x. However, before I do that, there's just one little thing I want to keep in mind, and that is if there's any k value in my trig expression. By a k value, I mean anything in front of my x, or the variable I'm trying to solve for. In this case, there is something in front of my x, this 2, and this 2 basically shrinks the period of a normal sine graph. So what I want to do is, as soon as I realize that I have a k value that isn't 1, I'm going to make a little statement here. I know that my k value is equal to 2, and that means that the period of my sine function, which is usually 2 pi, is going to be compressed by a factor of 2. So that means that I have a period of pi. This is important because I know that trig functions go on forever and ever and ever across the domain of x. So trig functions have an infinite amount of answers since they keep repeating certain values over and over again. The fact that the period is pi means that once I find some base value answers for my variable, I should be able to find more answers by adding or subtracting multiples of pi. So I want to keep that there. So once I find some answers, I can get myself more and make a more general statement for the solutions to this problem. All right. So now let's start working with how we're going to actually solve for x now that we've got our setup done. All right, so let's just make some room. We'll go on to a new page here. So I know the problem I'm trying to solve right now is sine of 2x minus 3 is equal to 2/3. And just things that I've set up. I know that my period is equal to pi, so I know how to get myself more answers once I find my base answers. And then I know I'm going to have answers in quadrant 1, where theta equals theta r, and quadrant 2, where theta equals pi minus theta r. All right. So the first thing I'm going to do is I'm going to let theta equal to 2x minus 3. Now I have the equation sine of theta equals 2/3. And this is very easy to solve for. All I need to do from here is find the related angle and then apply that related angle to these two quadrants here. When I'm finding a related angle though, what I like to do is I like to trick my angle into thinking that it's stuck in quadrant 1, because this way your calculator will always kind of read a nice related angle that's between 0 and 90 degrees. So what I like doing is I like saying that theta r is equal to sine minus 1 of the absolute ratio. Because if this were to be a negative ratio here, it would be a lot easier for me to make it an absolute value, to trick it to thinking it's going to be between 0 and 90 degrees. So I always want to basically, whenever I'm solving for a related angle, you want to always keep it positive, no matter what. So if I solve for theta r here, I'm just going to calculate it quickly on my calculator. We get that theta r is equal to, hang on guys, sorry about that. And I'm going to solve things in terms of radians. I get roughly 0.73. So we can now apply this related angle to our quadrants. I know that theta is going to equal 0.73. And here I know that theta is going to equal pi minus 0.73. Calculating that, I want to get the most approximate answer as I can. I get roughly 2.41. Okay, so these are our values for theta. However, we're not trying to solve for theta. We're trying to solve for x. So what I can do now is I can substitute the expression for x back in for theta. So if theta equals 0.73, that means that 2x minus 3 equals 0.73. And then I can solve for x here just by doing some simple rearranging. So if I move over the 3 and then divide by 2, I'm going to get that x is equal to roughly 1.87 radians. And in this case here, 2x minus 3 can equal 2.41. I'll do the exact same thing. X is going to be equal to 2.71 roughly. Okay, so we've got our base answers for x. We've solved the trig equation. However, again, trig equations go on all throughout the domain of x. So there's an infinite amount of times where sine of 2x minus 3 is going to have a ratio of 2/3. We know that the period is pi. So all we got to do afterwards here is just write down that our answers can be 1.87 plus any multiple of pi afterwards. Same thing goes for our other answer. And here we just need to kind of specify that n is an integer. It can be positive or a negative integer, but basically this is just saying that after 1.87 radians, every pi radians will get another solution for this problem. Same thing goes for the 2.71.
Well, there you have it, guys. Hopefully trig equations seem a little less scary now. If you still have a few questions about problems like these or want to provide us with some feedback, which I'd really appreciate, feel free to check out our Facebook page or drop a comment in the video and we will get back to you soon. If you enjoyed this video, feel free to share it with your friends and please smash that like button so we can help more students. And remember, whether you're struggling in school or just trying to get ahead of the curve, we have tons of amazing options available. Book a session with us now. I'll see you guys next time.